I bet that you've heard the term climate change before, and that you know it's a bad thing because it's causing polar bears to go on involuntary diets. I also bet that you vaguely understand that your car, or coal, or even cows are somewhat to blame for causing this, quote, climate change. But how? I mean, what can your car and a cow have in common? Well, if you drive a Chevrolet, quite a bit. Jokes aside, if you've read the title of this video, you already know what the answer to that question is, and that is greenhouse gases. But what is a greenhouse gas? Better yet, how do they actually work? Unfortunately, the answer to those questions is a little complicated and hard to distill into one sentence, which is why I've made this series where I explain science at 3 different levels. And I hope this helps people get value out of this video regardless of how much you know. And hopefully you can follow along as we progressively get more complicated. This, by the way, is the second video of the series, and if you want to watch the first one that explains the difference between weather and climate, you can click that up here. But without further ado, my name is Matthew. These 2 pieces of paper prove that I'm quite boring at parties, and you're watching Carbon Anonymous. Let's start by introducing Joseph Fourier, who, as you can see from this picture, is really old. And in the 1820s, unburdened by the distraction of Netflix, he decided that it would be fun to calculate the Earth's entire temperature. Because, I mean, it's the 1820s, what else are you gonna do? Now, for time's sake, I'm not going to explain how he did those calculations because all you need to know is that he got it wrong. I mean, he was way off. He calculated that the Earth should be freezing at minus 15 degrees Celsius, when in reality, it's actually a pretty balmy 15 degrees Celsius. Now that's 5 and 59 degrees Fahrenheit for you freedom lovers out there. But like all good scientists, Joseph asked himself, why am I wrong? And he proposed that the atmosphere acts as some sort of insulator, such that it traps more heat and artificially raises the temperature. Now, he didn't know that greenhouse gases were that insulator, but he was pretty close. And greenhouse gases work in a very similar manner to greenhouses, which is actually where the term comes from, because a greenhouse lets sunlight through because it's made of glass, but it traps heat. And greenhouse gases do the exact same thing. They let energy through, like sunlight, but they trap heat from radiating to space. Now, while a greenhouse is a good-ish analogy, one of the problems is that nobody has a greenhouse anymore, so I use a different analogy. In fact, I use blankets, because if you understand how a blanket keeps you warm, you also understand how greenhouse gases keep the world warm. When you're sleeping, your body's naturally radiating some heat. And if there isn't a blanket, that keeps you cold because the heat escapes quite easily. If instead you're wearing blankets, that heat becomes trapped, and that artificially raises your temperature. And that's very much what greenhouse gases do as well. They don't let heat escape, and that also artificially increases the temperature of the planet. So this Joseph guy found out that we actually need greenhouse gases because without them, it'd be quite cold. However, before you step away from this video and say, oh my god, this climate scientist just said that greenhouse gases are a good thing, let me clarify. The problem isn't that greenhouse gases exist, the problem is that cars and coal and cows and even deforestation have added way more of these gases to the atmosphere than there should be, which in effect is the same thing as putting more blankets on you while you're trying to sleep. And we all know how difficult it is to sleep when you have too many blankets on. Alright, so moving up a level, we're gonna have to move away from the analogies and actually start using some complicated terms. To understand how greenhouse gases work, we have to understand how the Earth receives and gets rid of energy. So the Earth receives the vast majority of its energy from the sun, specifically as visible light and ultraviolet radiation. Climate scientists, we typically refer to this as incoming shortwave radiation. Incoming as it's coming from the sun, and shortwave because it's very high energy. For example, high energy enough to cause sunburns, which is what UV radiation does. So this energy comes down, it warms up the planet, but this energy is then re-emitted in a different wavelength. Specifically, instead of being visible in ultraviolet, it's emitted as infrared radiation. And climate scientists typically call this outgoing long-wave radiation. Outgoing because it's leaving the Earth's system, and long-wave radiation because it's low energy. Low energy enough to no longer cause sunburns, which is why you don't get sunburns at night, if that already wasn't pretty obvious. And this is where greenhouse gases come in, because they do nothing to the incoming shortwave radiation. They let it through like the world's worst bouncer. They do, however, love absorbing that infrared, outgoing long-wave radiation. And note that I use the word they there because there are many different types of greenhouse gases. There is carbon dioxide, which comes from burning fossil fuels. There is methane that comes from cows and leaky gas wells. There's nitrous oxide that comes from agricultural activities. And there's even water, but I'll get to water when we get to the expert level. And what groups all of these molecules together is that they love absorbing infrared radiation. So in effect, this creates an imbalance, right? More energy is coming into the system and less can leave. And the only way to balance that out is to increase the temperature of the planet. So the Earth's temperature is pretty well correlated to how many greenhouse gases are in the atmosphere. Unfortunately for us, humans are added many more of these gases to the atmosphere, much more than there should be. And this creates a larger imbalance. Same amount of energy is coming in, but less can leave. And of course, if there's more energy coming in than out, that will increase temperatures and will ultimately cause climate change. All right, training wheels off, let's get technical up in here. We've established that greenhouse gases absorb infrared, right? That outgoing long-wave radiation. But what we now have to introduce is that all radiation exists on a spectrum, specifically what we call the electromagnetic spectrum. And this encompasses many things, whether it be X-rays, ultraviolet, visible infrared, microwave, radio wave. They're all the exact same thing, just at a different wavelength and frequency. The Earth, as we've established, emits in the infrared part of the spectrum. And if we were to put a satellite in space and measure how much of that infrared is making it to space, it should, theoretically, look something like this. A bell curve with a right skew to it. However, it doesn't look like that at all. Instead, it looks like this jumbled mess. But it's a jumbled mess that can only be understood because of greenhouse gases. Like we said, greenhouse gases absorb in this spectrum, so we'd expect that not all of that infrared would make it to space. And if this graph is measuring how much energy is escaping, we can see in real time how much of that energy is being retained because of greenhouse gases. But it really does look like a mess, so let's go back and look at the theoretical spectrum and then start adding in the different greenhouse gases to see what they do. Let's start by adding carbon dioxide, and you'll see that there is a very large dip around this 15 micron wavelength. Then we can add methane, and you'll see that there's another dip at the 7 micron wavelength. Arguably, carbon dioxide and methane are the two most important greenhouse gases that humans have added to the atmosphere. When we compare them to before the Industrial Revolution, before we really started burning fossil fuels, we can see that levels of carbon dioxide are up 50%, and methane has more than tripled. And when we update this graph to have the new concentrations of carbon dioxide and methane, you can see that those dips get a little bit deeper and a little bit wider, which indicate that even more energy is being retained within the system. However, the dips aren't that big, and quite frankly, the graph still doesn't look like the one I showed you before. And that's when we need to start looking at water. When we add water to this graph, we see that water absorbs quite a bit. In fact, it absorbs more outgoing radiation than carbon dioxide and methane combined. So then why aren't climate scientists freaking out about water? Well, we do, but for different reasons when you compare it to carbon dioxide and methane. And that is because humans aren't adding a huge amount of water to the atmosphere. The vast majority of water that gets into it comes from evaporation because the world is covered by 70% oceans. However, the amount of moisture, right, water vapor that the atmosphere can hold is dependent on temperature. And because we've added carbon dioxide and methane to the atmosphere, we have increased temperatures slightly, or at least enough to make it so that the atmosphere can carry just a little bit more water vapor. And because water vapor is a greenhouse gas, that amplifies the initial warming. Essentially, this is a positive feedback. And I can tell you right now, there are other positive feedback loops that are affecting the Earth's climate, but those are for another time because even though greenhouse gases are extremely important, they are not the only thing affecting the Earth's atmosphere and the Earth's climate. So stick around or subscribe if you want to see those future conversations. But I think it's now time to segue to our conclusion. All right, so to conclude, what is a greenhouse gas? It is a gas that, much like a blanket, traps heat. And although we need them to survive, because without greenhouse gases, the world would be a much colder place, we can't have too much because then it'd also be too warm. We're very much in a Goldilocks situation here. We also covered how greenhouse gases work, right? Of course, the effect is they trap heat, but they do that by letting incoming shortwave radiation through and trapping or absorbing longwave outgoing radiation, which creates this energy imbalance that traps that heat. And as we've seen, even though we have increased the level of CO2 and methane in the atmosphere, there are these secondary positive feedbacks that are actually amplifying climate change. Well, there you go. That is how greenhouse gases actually work at 3 different levels of science. My name is Matthew. You've been watching Carbon Anonymous. If you've learned something from this video, please give it a like, give it a comment, and also make sure to subscribe because that helps a lot. And lastly, thank you for watching.